Welcome to Chapter 4. Today we're going to focus on the first two sections of Chapter 4, looking at exponential and log functions. We've talked about some functions already, how to evaluate, how to graph, how to find intercepts. Today we're going to add two more functions to that toolbox in exponential and log. So you can read these goals here. Today is basically a lot of definitions and a lot of form work, looking at how this form and that form are equivalent. We're going to start off by talking about exponential functions in what we call standard form. So this is standard form for an exponential function. Now what makes this different than a quadratic function? Well, in a quadratic function, our base is our variable and our exponent stays the same. In an exponential function, our exponent stays the same our base stays the same. Our exponent is what is going to change. So b to the x power, or base to any power of a variable, is what we consider to be standard form. In order for it to be exponential, this base cannot be 1, because 1 to any power is still going to be 1, so that's not going to change. Okay, our base also in standard form would have to be greater than 0. When an exponential function is in standard form, its domain is always going to be all real numbers, meaning we can plug in any real number x. Whatever number we plug in, however, for x, if it is in standard form, our range will be from 0 to infinity. Notice that parenthesis there means that 0 is not included, so our range is going to be any y value greater than 0. Okay? All graphs will pass through the point 0, 1. That's because if our exponent, no matter what our base is 0, any base to an exponent of 0 has a value of 1. So when x is 0, y has to be 1. Our graph will never cross the x-axis. That's representative right here. The x-axis is what we call an asymptote, meaning that it will never ever cross the x-axis, but it will get closer and closer and closer to it, whether it's smaller or on the right side of the x-axis, meaning my x's are bigger, is just dependent on what our base is. So if our base b is greater than 1, our graph is what we consider an increasing function, meaning it will have a smooth curve up, and I'll show you that here in a minute. If our base is between 0 and 1, meaning it's greater than 0 but less than 1 or a fraction, we call it a decreasing function, and that means it will go down from left to right. So what does that look like? So if I just sketch a couple quick xy coordinate planes, okay, this is what we would consider to be a decreasing function. It goes down from left to right. This is what we consider to be an increasing function. It would go up from left to right. So this is when we would have our base greater than 1. This is when our base would be less than 1, but greater than 0. Okay, decreasing function, increasing function. If we're dealing with functions whose base remains constant and our variable changes, we're going to have to review a couple rules for exponents. Okay, remember that if an exponent is negative, let me fix that. I don't like the way that looks. If my exponent is negative, b to the negative n power, then to make an exponent positive, we would move that term to the opposite position of a fraction. Now, why do we do that? Well, we can't really evaluate a negative exponent without a calculator. So we would have to make it positive in this fraction in order to evaluate it. So vice versa, if we have a negative exponent that starts in the denominator, I can move it up to the top, and that term will now become a positive exponential term, which then means I can evaluate it. So what does that mean? Well, a lot of times our base is going to be a fraction. Anytime we have a fraction raised to an exponent, that means both the numerator and the denominator take on that exponent. Well, what if that exponent is negative? Well, then that means a to the negative m over b to the negative m, and then we would have to switch those to make those exponent terms positive so that we can then evaluate the numerator and the denominator. Okay? We're going to start by graphing. This is the first time in this class we're actually going to graph. So when they say graph the function, we recognize this is an exponential function. Because these are in standard form, I'm going to ask you to use these 5 domain values or x values to find our y values. Okay, so our function, our f of x, is 1/3 to the x power. Okay, I'm going to start with the ones that we know. We know that if these are our x's, I can plug that in for the exponent. 1/3 to the 0 power, we know anything to the 0 power has a value of 1. So if I plugged in 0, I get the output of 1. So I have an ordered pair of 0, 1 that I could plot. I'm going to do the same thing with my positive exponents. 1/3 to the first power is 1/3. So when I plugged in 1, I got the output value or y value of 1/3. 1/3 squared either means 1/3 times 1/3, or you can use the exponent rule we just talked about, which would mean 1 squared over 3 squared, which would be 1/9. So I plugged in 2, and I got the y value of 1/9. Now what do these look like? We just talked about it. 1/3 to the negative second is going to mean 1 to the negative second over 3 to the negative second. That does not mean -1 over -9. That means we have to make these exponential terms with negative exponents positive. So I'm going to move the 1 on the top down to the bottom and become 1 squared, the 1 on the bottom up to the top and become 3 squared. Now that these individual exponential terms are positive, I can evaluate them. 3 squared is 9, 1 squared is 1. So when I plugged in -2, I got out 9. Let's do the same thing with -1. 1/3 to the negative first means 1 to the negative first over 3 to the negative first. We're going to switch those, 3 to the first over 1 to the first, and I get 3. I get -1 and 3. Okay. We would then need to graph these. You can make a quick sketch of our graph, XY coordinate plane. We picked x values -2, -1, 0, 1, and 2. When I plugged in -2, I got 9. Plugged in -1, I got 3. 0 is at 1, 1 is at 1/3, and 2 is at 1/9. So we have a smooth curve moving down from left to right. Notice that my graph is never going to touch this x-axis. It'll always get closer and closer and closer to it. So this would be the graph of 1/3 to the x power. Sorry about my dog. All right, you are going to need a calculator for this point. Remember me saying on day 1, excuse me. If you remember me saying at the beginning of the semester that you will need a calculator and that it had to do exponents, this would be the reason why. There are going to be some things in this chapter that you cannot do without a calculator. This would be one of them. Evaluating exponential terms that are not traditional, meaning that we don't really understand what it means to take 4 and raise it to the 2.6 power. We know taking 4 to the 2 power, 16, but what else does that mean? So we have to have a calculator. We're going to evaluate. They will tell you on my math lab what decimal place. I'm telling you to the 3rd decimal place. So however your calculator evaluates exponents, plug in your base of 4 and your exponent of 2.6. You're going to get 36.7583. Now I put that 4th decimal down there because that's what's going to determine what this 3rd decimal place will do. Remember, this number has to be a 5 through 9 to make that number go up. 1 through 4 will keep that number the same. So the correct estimation would be 36.758. The next one, 5 raised to the square root of 3 power. We're going to get 16.2424. Okay, so that 4 tells that 2, you're going to stay a 2. So 16.242. Okay, the only way you can get those correct is to have a calculator and know how to round properly. Okay. Let's move on to logarithms. Why do they put logarithms and exponentials in the same chapter? Well, that's because a logarithm is an inverse, which we know means the opposite of an exponential function. So if our exponential function in standard form is f of x equals b to the x power, we know that f of x can change to y. So the first part of finding an inverse, which we learned in chapter 2, is going to be to switch the x and the y terms. This is how the book writes it. I prefer to write it like that. These are the same thing. So the inverse, we're not going to solve for y because we can't really do that right now. But if this is our standard form of an exponential function, then the inverse in exponential form is x equals b to the y power. Now this, written as a log, we call this log base b, because our base of the exponential term is b, of our answer x will equal our exponent of y. We're going to have to work back and forth between these two terms, not only to find the values of logs, but also to help us solve equations later on down the road. Okay, so let's try working back and forth here. We're going to start with our logs and work it back into exponential form. We read this log base 7 of 343 equals 3. All three positions here are numbers. So if they're all numbers, when we put it in exponential form, we should have an equivalent answer. So our log base 7 is telling us the base of our exponential term is 7 of 343 equals 3. Remember, this is our base. This is our answer to our exponential expression. And this always represents our exponent. So we're going to have 7 cubed equals our answer of 343. If you evaluate this exponential term of 7 cubed, it does equal 343. Second one, log base b of 25 equals 2 is going to be base b to the second power equals 25. Now I'm not solving this right now. I'm just working back and forth between the form of logs and its equivalent exponential form. So the third one here, log base 4 of 16 equals y, it's going to be 4 to the y power equals 16. Now we are going to be using our knowledge of exponential form of logs to help us evaluate logs here in a minute. Let's use these and go the opposite direction. Now let's write these exponential forms in the equivalent log form. So 2 to the 5th power equals x. Log base 2 of our answer x equals our exponent of 5. And again, we're not solving anything, we're just writing this back and forth. The second one here says 27 equals b cubed. If you want to turn it around like this, you can. That will help you determine this is a log of base b of our answer 27 equals our exponent of 3. Now let's use that to find the value of each log. Now I've turned these into an equation. My math lab won't. This equation, we're looking for the value of the log sits here. But we know in exponential form, the number that sits here is our exponent. So if I can turn this log, I'm saying 2, base 2, to what power equals the answer of 16, that helps me determine that if x is 4, then this log base 2 of 16 has a value of 4. This value here is what we're looking for. We will be using this in equations here down the road. Second one, log base 5 of 1 over 125 equals x. So now I'm trying to determine 5 to what power equals a fraction 1 over 125. Well, in order to do this, we're going to have to do something here with this fraction. So I'm going to convert the denominator of 125 to 5 cubed. We all agree that 5 to the 3rd power equals 125. These two expressions are equivalent. Now, if this is a base 5 here in the numerator and this is a base 5 here in the denominator, then don't our rules of exponents tell us that I could move that base 5 to the 3rd power up to the top? but I would have to change that exponent to a negative. That would then tell me, in order for these two exponential expressions to be equivalent, if this is an exponent of negative 3, this x is going to have to equal negative 3. Therefore telling us that log base 5 of 1 over 125 equals the value of negative 3. This last one here also has a rule involved in it. If we write it the way it's written, this is the base 3 to what power equals the 7th root of 3. Well, we haven't really worked at 7th roots, but we have worked with cube roots and square roots. The root of this says any root can be written as an equivalent exponential function. The base of the root is a. The exponent inside here, we'll just call that m, becomes the numerator of our exponent. The type of root becomes our denominator. So if I'm looking at the square root of a, that's going to be the same thing as a to the 1/2 power. If I'm looking at the 4th root of a cubed, that's going to be a to the 3/4 power. So in order to solve this logarithm and find its value, I have to be able to convert the 7th root of 3 to 3 to the 1/7 power. Now I've got an expression where both sides are a base 3. This one has an exponent of 1/7. In order for these two to be equal, x is going to have to equal 1/7. So log base 3 of the 7th root of 3 equals 1/7. Okay. We're going to skip these next two. You won't really have any like that in your homework. The last thing we're going to talk about is some special types of logs. All these logs that we have looked at are just called normal logs. There's nothing special about them. But when we have a log that has a special base called a base e, then it does become something special. E is like pi in math. It's a constant. It's something that is accepted as math as a specific number. Okay, this is what e represents, and if you would type it in your calculator, it's going to be something equivalent to that number. Now on your calculator, you should have an log and an ln key somewhere in your calculator. If you look above your ln key, you will see an e to the x power. That is the button you will use when you are calculating the base e to any exponent. So I'm going to hit my second key. Some of you, it's going to be an alternate key, so that I can hit my ln and it shows on my calculator e to an exponent. I type in 3.4 and I get 29.9641. So if I'm rounding to 3 decimals, that's going to be 29.964. You may also have a plain e above your division sign. So if you want to use just the plain e, you could hit second division. That would type an e into your calculator, and then you can just use your exponent key for 3.4 if you would like. Okay. So to make things more complicated, when we are dealing with logarithms whose base is e, which is what we just talked about, you will never see that written. Log base e in logarithms is going to be reflected as an ln. That's because logarithms with a base e are what we call natural logs. Now why it's ln and not nl, I don't know that answer. But anytime you see an ln, you have to understand that if I'm then looking at the equivalent exponential form, my base of that is going to be e. So as an example of that, if I have the exponential expression e to the y power equals 33, and I want to put it in log form, normal log form would say log base e of our answer 33 equals our exponent of y. That would not be accepted because this log base e needs to be converted to its natural log form of ln. So we would take out log base e and leave the rest the same. So natural log of 33 equals y is telling us that we have e to the y power and an answer of 33. Because natural logs are special, they will have properties. We will be using these when we are expanding and condensing logs as well as solving log equations. Okay, so the natural log of 1 will always have a value of 0. So anytime you have a natural log of 1 in an expression, you can take it out and replace it with its value of 0. The natural log of e equals 1. The natural log of e to any power of x will equal that power of x. So what will that look like? Say I have the natural log of e to the 10th power. Well, if natural log of e to any power of x equals that power of x, then this will have a value of 10. So the natural log of e to the 17th power would equal 17. The last thing we're going to talk about today is another type of special log, which is a common log. A common log means the base of our logarithm is 10, or that means the base of our exponential expression is 10. Okay, so log base 10 of x, you will never see it written like that. You would see log of x, and we read that common log. Okay, so when there is no base between the word log and your answer or your other value there, we assume that that is a 10. Okay, so if I have common log of x equals y, for example, that's going to be 10 to the y power equals x. Okay, we don't see the base 10, we have to assume and understand it is there. Similar to natural logs, common log properties are that the common log of 1 has a value of 0, common log of 10 has a value of 1. If you're watching this video, please keep my birthday of August 10th in your mind for extra credit somewhere down the road here in class. The last log here is that the common log of 10 to any power of x will equal x. So an example of this, we can do this multiple ways. We're looking for what is the value of this log. Well, we know that this means common log of 10, or common log base 10 of 1,000 equals what? We could say 10 to what power equals 1,000, and we know that that is going to be 3. So this would have a value of 3. The other way we could look at this is we could use this property right here. We could convert 1,000 to 10 cubed, and we could use this property. Common log of 10 cubed by property equals 3. Your homework will be my math lab. It will be due on Thursday like normal. I will take attendance using this video, so please make sure you are taking notes just like you would in normal class so that we can move along and not have any issues. If you have any questions, please send me an email. Let me know. Have a good day.